Welcome to ReneEnergy.com on YouTube, the hub for all things renewable energy and sustainability. Our channel is dedicated to bringing you the latest innovations and insights in green energy, including cutting-edge developments like green hydrogen. Whether you're a sustainability veteran or just beginning your journey, we have something for everyone. Join us on this channel to explore inspiring projects for a sustainable tomorrow. We bring you the latest in renewable energy, sustainability, and cutting-edge technologies. And don't forget, for more in-depth information and resources, visit our website and subscribe to our newsletter for the latest updates and exclusive content. Electrolysis stands at the center of the green hydrogen revolution, but running electrolyzers cost-effectively and reliably requires more than just hardware. It demands real-time optimization, predictive maintenance, and data-driven insights, exactly where AI shines. In this episode, we'll dive into how machine learning and advanced data analytics supercharge hydrogen production. You'll learn how AI can boost electrolyzer efficiency by 20%, predict and prevent equipment failure, and accelerate catalyst discovery, driving down costs and unleashing scale. At its core, an electrolyzer is an electrochemical converter that splits water into hydrogen and oxygen using electricity. The two most common types today are alkaline and proton exchange membrane (PEM) electrolyzers. While alkaline systems are robust and economical, they respond slowly to changing power inputs. PEM electrolyzers, favored for coupling with solar and wind, offer fast dynamic response and high current densities. But no matter which technology you choose, operating an electrolyzer involves juggling dozens of variables: stack voltage, current density, water flow rate, temperature, pressure, and ancillary equipment like pumps and heat exchangers. Traditionally, operators rely on fixed set points or human-driven adjustments to balance production and maintenance schedules. But this approach cannot match the speed and precision of machine learning models trained on live operational data. Let's start with efficiency optimization. AI systems ingest real-time sensor data, voltage, current, temperature readings, water purity metrics, and even vibration signals from pumps. By applying supervised learning algorithms, engineers can map how slight changes in operating conditions affect performance metrics like hydrogen output per kilowatt-hour. These high-fidelity models then run in real time to identify optimal operating points, adjusting current density up or down by increments of a few milliamps to extract maximum hydrogen with minimal energy waste. Siemens Energy reports efficiency gains of around 20% on their PEM electrolyzers after deploying machine learning models that continuously fine-tune stack parameters based on incoming data and weather forecasts. Over the lifetime of a 100 megawatts electrolyzer plant, these efficiency improvements translate into millions of dollars saved in electricity costs. Another critical AI application is predictive maintenance. Electrolyzer stacks degrade over time due to catalyst poisoning, membrane wear, and cell imbalance. Unplanned downtime can be catastrophic. A single cell failure in a 100 megawatts plant can force a partial or total shutdown while maintenance crews troubleshoot and replace components. By training machine learning models, such as random forests or gradient boosting machines, on historical failure data, engineers can identify patterns that signal impending trouble. For example, a gradual uptick in cell voltage variance, combined with subtle changes in stack temperature distribution, may forecast membrane thinning or electrode delamination weeks before a critical failure. Once flagged, operators can schedule maintenance during low production periods, minimizing disruptions and extending stack lifetimes by 20 to 30%. Digital twins, virtual replicas of physical electrolyzer systems, take predictive maintenance further. These physics-informed models simulate an electrolyzer's behavior under varying loads, temperatures, and water quality conditions. By calibrating these simulations with real-time data, engineers can run what-if scenarios. How would a sudden spike in inlet temperature affect stack performance? What if the grid sends intermittent power due to low wind? Digital twins accelerate design optimization by allowing rapid prototyping of new control strategies without risking the live plant. Moving upstream in the value chain, AI is instrumental in catalyst discovery, the holy grail for reducing electrolyzer capital costs. Today's PEM electrolyzers rely on precious metals like platinum and iridium, which are expensive and scarce. Using high-throughput computing, data scientists feed materials databases into machine learning models, such as convolutional neural networks trained to recognize atomic structures, and screen hundreds of thousands of candidate catalysts. These algorithms can predict key properties like hydrogen overpotential, stability under acidic conditions, and cost metrics. By narrowing the search space from millions of potential combinations to a few thousand promising candidates, AI accelerates lab testing cycles. Recent breakthroughs, such as AI-identified nickel-iron catalysts that exhibit comparable performance to platinum at half the cost, demonstrate the transformative power of data-driven materials science. AI also optimizes upstream operations, such as water purification and pretreatment. Electrolyzer feedwater must meet strict purity thresholds. Impurities like chloride ions or silica can corrode components and accelerate degradation. Machine learning models analyze water quality sensor data, adjusting ion exchange resin regeneration schedules, membrane filter replacements, and pH stabilization protocols in real time. By predicting shifts in feedwater composition, due to seasonal groundwater changes or industrial discharges, AI ensures that water pretreatment systems operate just in time, reducing OPEX and preventing unplanned shutdowns. Finally, AI manages the interface between electrolyzers and renewable energy sources. Wind and solar power are inherently variable. Wind speeds can plummet within minutes, and cloud cover can drop solar output by 70% in seconds. Without intelligent coordination, electrolyzers can either overreact, ramping down too quickly and wasting potential hydrogen output, or operate inefficiently under suboptimal power. AI algorithms ingest weather forecasts, real-time renewable generation data, and electricity price signals to orchestrate dynamic load following. When wind speeds surge at 2 a.m., the AI dispatches electrolyzers to ramp up, capitalizing on the lowest energy prices. At midday, if solar spikes above grid demand, electrolyzers soak up extra power. Conversely, during extended load generation periods, AI may recommend operating at partial load to preserve stack integrity rather than shutting down entirely. One emerging concept is virtual power plants that aggregate multiple electrolyzer facilities across a region. AI optimizes hydrogen production schedules across these sites, treating them as a flexible resource that can fit into energy and ancillary service markets. For instance, a 100 megawatts electrolyzer in Texas could reduce output when a nearby solar plant dips, while a 50 megawatts plant in New Mexico ramps up, maintaining regional grid balance. AI performs this coordination in milliseconds, far beyond human capacity. By now, it's clear that AI and electrolysis form a virtuous cycle. AI drives electrolyzer efficiency and reliability, while cheap green hydrogen provides the dispatchable power data centers need to support AI workloads. As electrolyzer OPEX falls, from electricity savings achieved via AI optimization, and CapEx declines through AI-accelerated materials discovery, the cost of green hydrogen edges closer to, or even below, that of gray hydrogen. This economic tipping point will unlock new markets and create a feedback loop. More hydrogen projects justify larger AI-driven optimization engines, which in turn lower costs further, accelerating global adoption. In Episode 5, Smarter Storage and Logistics, AI and Hydrogen Supply Chains will expand our view down the value chain. We'll explore how AI forecasts regional hydrogen demand among industrial off-takers, optimizes transportation routes for compressed or liquefied hydrogen, and ensures safety through advanced leak detection systems. You'll learn about AI-powered pipeline integrity management and how digital marketplaces can match buyers and sellers of hydrogen, leveraging blockchain for transparency and trust. Before we close, here's your quick action item. Explore how predictive analytics could help your own processes. If you're an electrolyzer OEM, consider integrating AI-based stack health monitoring into your service offerings. If you're a project developer, think about partnering with data analytics firms to model regional renewable generation profiles and optimize plant siting. Download our green hydrogen digitalization checklist, available on renewenergy.com, to see a roadmap of AI tools and data sources you'll need for a successful hydrogen production project. Thank you for watching Episode 4 of Why Green Hydrogen is Critical in the Global AI Race. Don't forget to subscribe, click the notification bell, and drop a comment telling us which AI application, predictive maintenance, digital twins, or materials discovery you find most exciting. We'll be answering questions and sharing additional resources throughout the series. Join us next time as we examine how AI makes hydrogen supply chains smarter and more resilient. Until then, keep innovating, stay data-driven, and remember, the future of hydrogen depends on the power of AI to unlock its full potential. Thanks for tuning into the renewenergy.com YouTube channel. We trust you found this episode enlightening and motivating. There's a world of innovation and opportunity in sustainable energy, and we're delighted to share this journey with you. Stay in the loop with the latest on renewable energy and sustainability by visiting our website and subscribing to our newsletter. Your support is immensely appreciated, it's truly invaluable to us. Don't miss our next video on new trends in renewable energy. Follow us on social media for the latest updates. Enjoyed the video? like, subscribe, and share for more green insights. Thanks for watching.